Okay, so this is a continuation of quantum theory, wherein here we are going to discuss Compton effect, and also photoelectric effect. So let's take a look at Compton effect first. What is Compton effect? So Compton effect is that if you have here an incident photon, so let's say we have here an incident photon, then you have a target electron which was initially at rest. So it's like you imagine in elastic collision, we have billiard balls. For example, we have billiard balls. Then this one is initially moving, but the other billiard ball is at rest. When this collided with this one, either it can transfer all its momentum to this so that this will have its velocity, but this will have no final velocity. So this, it will be at rest and then this will move. Or they can also be moving with a particular velocity. But if we are going to have the Compton effect or the Compton scattering, that is, you have an incident photon, okay, h mu, and then it collided with an electron. Because in quantum theory, photon is considered to be a particle, or light is a particle, and we have photons. So we have photon there colliding with electron. What will happen is that photon will be scattered. So here, we have the photon here, okay, h mu final, and then we have here the electron will also move, having a velocity and then having a momentum mv. Now this one has an angle phi, and then we have here angle theta. So that is Compton scattering. Now we are going to discuss the different factors which can affect the wavelength or the initial wavelength of the photon and then the final wavelength of the scattered photon. So what will happen to the wavelength and what will happen to the energy? Any guess? So you can expect that the energy will be lowered. Then of course the frequency will also, or you can expect that the energy will be lowered and the wavelength will be changed. So let's take a look at this. Compton scattering was discovered by Arthur H. Compton. This one confirmed the quantum nature of X-rays. X-rays strike matter, and some radiation is scattered after striking a matter. And also scattered radiation has smaller frequency. When we say smaller frequency, it has lower energy. And then the change in wavelength depends on the angle through which the radiation is scattered. So this depends on the angle through which the radiation is scattered. Let's take a look at this equation. You have here the final wavelength is equal to the initial wavelength plus Planck's constant divided by the rest mass, and then we have here the speed of light, then multiplied it by 1 minus cosine phi. What is this angle? This angle is the scattering angle. So you have here the photons, and then this is your angle phi. So the change in the lambda or the change in the wavelength will be dependent on this angle. So let's complete this equation we have here. Or let's take a look at the constants we have here. Lambda prime minus the initial lambda or the initial wavelength is equivalent to the Planck's constant 6.626 times 10 to negative 34 joule second divided by the mass. We have the let's use 9.11 times 10 to negative 31 kilograms. And then you have here 3 times 10 to the 8th meters per second. So that is the speed of light. Okay, this value is equivalent to 2.426 times 10 to negative 12 liters. So this equation here, or this value here, has a dimension or has a length dimension. So let's take a look at the cancellation of units. Okay, joule again is Newton meter, or we have kilogram meter per second squared. Okay, joule is kilogram meter per second squared. That is for Newton, and then you have to multiply second divided by kilogram, and then you have meters per second. So let's check. You can cancel out 1 second here, and then the other second here, and then cancel out kilograms. So the unit here, the final unit would be in meters. Okay, so this one this one has a unit of length or unit of meters. If we are going to analyze in the classical theory, according to this, scattered wave will have the same velocity as the incident wave. But you can see in the explanation in Compton Scattering that the wave will have different wavelength after being scattered. So according to quantum theory, collision of two particles, we have the incident photon and the electron, or the incident photon will collide to the electron, which is initially at rest. So quantum theory describes this phenomenon as collision of two particles. Okay? Compared to classical theory, the wavelength is expected to be the same. But in quantum theory, it is expected that the wavelength will change. So this is the experimental setup. For example, you have here the X-ray tube. So we have molybdenum. And then you have a carbon target. Then you have the detector. So you can see here at different angles, you have different wavelengths. So you have different waveforms. So let's take a look at this one closer. Now, the intensity here. Okay, now look at this. It has two peaks. You have here the initial wavelength, and then you have here the final wavelength. Again, this is the initial wavelength and the final wavelength. Initial wavelength and the final wavelength. If you will observe here, this has higher wavelength. So if that has higher wavelength, therefore the energy has decreased for the wavelength of the scattered photon. If you're going to look at this one also, this has higher wavelength compared to this wavelength. So again, since let's recall the relationship between wavelength and energy. The longer the wavelength, the lower the energy is. The smaller the wavelength, the higher the energy is. So that means that the photon has lost some of its energy because it was acquired by the electron, which has also gained momentum. Okay? So when wavelength of X-ray is scattered at a certain angle, they are measured. The curve of intensity per unit wavelength as a function of wavelength has two peaks. So because of those two peaks observed, so we can now say that the wavelength has changed. Unlike in the classical theory that the wavelength is not expected to change. Okay, again, we have already discussed about Max Planck, wherein Planck considered energy as packets of energy, or that energy is quantized. So it doesn't exist in a continuous manner. So it's a multiple integer of a particular energy. So that's why we have the Max Planck's constant h. So the energy of the photon is hf. H is the Planck's constant, and then f is the frequency. But as I have mentioned, it's not continuous. Now, 5 years later, we have here Albert Einstein. wherein Albert Einstein also considered that beam of light consists of small packets of energy, that energy is not continuous, but it's also quantized, and the one carrying that energy are photons or quanta. That is according to Einstein. So we have here, the energy is described as energy h times the frequency, wherein h here is a Planck's constant equivalent to 6.2660693 times 10 to negative 34 joules second. And then the energy of a photon, we have frequency. Let's recall the relationship between speed and frequency. We have here V equals lambda F. And then since we are referring to light, we have C for the speed of light, lambda F. So frequency can be expressed as C over lambda. So the energy now could be expressed as H, the Planck's constant. Then F is equivalent to C over lambda. So we have hc over lambda. This is the energy of a photon. Okay, so that is Einstein's photon explanation. That, for example, if a photon arrives at a surface, it is absorbed by the electron. It's all or nothing. You cannot get portion of the energy of the quanta. You have to get all the energy of the photons or the quanta. All energy are being transferred. It's not a continuous transfer of energy. It's not possible to transfer 1/2 of the energy of photon, 1/4 of the energy of photon, but the whole energy that the photon has will be transferred. Now, what happens here if the energy now would be greater than the work function? I'll show you an equation for this. I'll show you the equation first. We have the K maximum, or the kinetic energy, the maximum kinetic energy is equal to 1/2 mv maximum squared. Okay, this kinetic energy maximum should be equal to hf minus the work function phi. So we also have an equation wherein Ke maximum is equivalent to electron times the stopping potential. Or if you may recall, in your electricity is analogous to this one. We have U or potential energy is equivalent to Q, the electric potential. So it's like that. If we are going to equate this, we have Ke maximum hf minus the work function to this. We have hf minus work function is equivalent to electron. Then we have the stopping potential or the electric potential. Okay, so we will have that equation. What do we mean by this one? Okay, the maximum energy that it can transfer would be amounting to hf, which is the energy of the photon, minus the work function, this work function. Okay, take note here that the work function phi or phi, this is the minimum energy. Okay, that is the minimum energy so that an electron can be removed from the surface. So here again, this is the energy of the quanta or of the photon, and then this one is the work function or the minimum energy that it has to have so that the electron will be released. Okay, now let's talk about photon momentum. Recall in the previous discussions that we have, wherein we have relativistic energy and relativistic momentum, we have the energy for photon. Since it's a massless particle, the energy for photon is equivalent to Pc. So here, the momentum is equivalent to energy divided by C. Recall that the energy of the photon is equal to hf, then divided by C. And then looking at this, let's recall the relationship again. C equals lambda f. So C over f is equivalent to lambda. So this is the reciprocal. So f over c, therefore this one is over lambda. We now have the photon momentum is equivalent to h over lambda. So this one is the momentum of the photon. This is the energy of the photon. And then this is the kinetic energy or the maximum kinetic energy, okay, that the electron can have. Now let's look at how the wave theory will explain photoelectric effect. When intensity and frequency of light wave are varied, the wave theory makes the following predictions. If the light intensity is increased, then the number of electrons change, or when intensity and frequency of light wave are varied, the wave theory makes the following predictions. If the light intensity is increased, the number of electrons ejected and their maximum kinetic energy should be increased, because the higher intensity means a greater electric field amplitude, and a greater electric field should eject electrons with higher speed. So light intensity is increased here, therefore maximum kinetic energy is increased, and then that will lead to that electrons will have higher speed. Number 2, the frequency of light should not affect the kinetic energy of the electrons. Only the intensity should affect the maximum kinetic energy. But if we are going to look at the photon theory, so looking at this, an increased intensity of light means more photons are incident. So again, increase in the intensity, that means more photons are incident to the electron. Therefore, it follows that more electrons will be ejected. Okay, since there are more photons which are incident to the electrons or to the material, therefore it follows that more electrons will be ejected. But since the energy, take note, energy of the photon is not changed. The maximum kinetic energy of electrons is not changed. Unlike in the wave theory, that the kinetic energy can change. Okay, so take note of that. It's contradictory to the photon theory. Then number 2, if the frequency of the light is increased, the maximum kinetic energy of the electrons increases linearly. So it's not because of the intensity of the light beam, but if the frequency of light is increased, maximum kinetic energy of the electron increases according to the following equation. So it is dependent on the frequency of light. Okay? Unlike previously, looking at this, look, the frequency of light should not affect the kinetic energy. But in photon theory, the frequency of light is the one responsible to change or to increase the maximum kinetic energy. Okay? But looking at number 3, if the frequency is less than the cutoff frequency, where hf naught equals work function naught, no electrons will be ejected at all, no matter how great the intensity of light. Okay, so I want you to take note of this one also. As we have mentioned earlier, it has to have the energy of light, which is hf, or the energy of the photon hf, minus the work function. You have to meet the work function or the energy, the minimum energy, so that the electron can be removed from the surface. So if the electron is less than the cutoff frequency, then no electron will be ejected, no matter how you increase the intensity of light. So it will be dependent on the frequency. Okay? So these topics are actually hard to absorb, but just try to repeat understanding the concepts, and then you will be able to understand this. If you survive the relativistic theory or relativity, special relativity, those concepts, and you were able to derive the equations associated with relativistic energy, relativistic momentum, you will also be able to understand this. Okay, next. Now let's talk about the interactions that photons can undergo if it will have or it will meet an electron. Number one, the photon can be scattered off an electron and in the process lose some energy. So we were able to explain this one. A photon can be scattered, and then in the process it will lose some of its energy. That's why the wavelength will increase. This is Compton effect. But notice that the photon is not slowed down. Okay, it will still travel at a speed c. Unlike if you have classical mechanics, if you have the collisions of billiard balls, you know that the other ball, after ball 1 transfers energy to the other ball 1 will slow down. Unlike in photon, it will not slow down, so it will still travel at the speed of light c. Okay. Next is the photoelectric effect, where in a photon, if you shine light on a surface, and then it can eject electron out of the atom, and in the process, the photon itself disappears. Okay. That's another interaction. Okay, here, this is the Compton interaction, which was explained earlier. This is the photon, or this is the Compton interaction, which was explained earlier. So you have here, number one, if you shine, or if you have photon, it can eject that electron from the atom because it will gain kinetic energy. Another one is a photon can be scattered after colliding with an electron. The electron will also gain kinetic energy, then the scattered photon will have longer wavelength. That is another interaction. Next, the photon may knock an atomic electron to a higher energy state in the atom if its energy is not sufficient to knock the electron out altogether. In this process, the photon also disappears, and its energy is given to the atom. Such atom is then said to be in an excited state. Let me show you an illustration of that. For example, here, if you have the energy of the photon, the electron is at energy level 1, and then it can, because of that energy, it can jump to because of the energy of the photon, it can jump to a higher level. So this one is the excited state, because it has gained the energy coming from the photon. Okay, so that is another interaction. And that energy should be equal to this, the difference in E2 minus E1. Okay, next. Another thing that can happen is this, pair production. Okay, another interaction could be this, pair production. A photon can actually create matter. Take note, photon has no mass. Okay, photon is a massless particle but it can create matter and antimatter because of the energy that it has. So that is another interaction that a photon can have when meeting an electron. So a photon can actually create matter, such as the production of electron and a positron. A positron has the same charge, or a positron has the same mass as the electron, but the opposite charge is positive E. So from energy alone, matter can be created, or electron and positron can be created. So that is another interaction of photon. Okay, to summarize, we have this one. Transmitted, it is not affected. The transmitted photon, okay, the incident photon, then it will have the same energy. The next one is collision with a tightly bound inner shell electron. So photoelectric absorption. The energy of the photon can be absorbed by the electron. And then you have here Rayleigh scattering, elastic collision with a bound outer shell electron. And then you have Compton scattering, which is the inelastic collision with weakly bound outer shell electron. So those are the interactions a photon can have. Okay. Okay, next. Is light a wave or a particle? So that is the major question here. Now, in your waves and optics, we have discussed some properties of light which support that it's a wave. And there are also some properties of light that support that it's a wave and a particle. For example, we have interference and diffraction and polarization. So those are some properties of light wherein it supports that light is a wave. But light as a particle is also supported by reflection of light, is supported by photoelectric effect. So which is which? Now according to Niels Bohr, we have here the principle of complementarity, that items can be analyzed separately as having contradictory properties. So since they are both correct, we can look at light with the different properties of light as a wave, but we can also look at light as a particle, but we cannot combine them. So we can never have the same description at the same time. If we will look at light as a wave, so those are the different properties of light telling us that it's a wave. If we are also going to look at light as a particle, we also have the different properties of light supporting that light is a particle. So they are the wave description and the particle description. They are complementary. So we need both of them so that we can properly discuss light. Okay, so that is according to Niels Bohr. Okay, so let us now solve some sample problems. Number 1, calculate the energy of a photon of blue light with a wavelength of 450 nanometers. So take note that the energy it has, the energy is equal to hf, and then frequency, we have here c equals lambda f. So our frequency is just c over lambda, so we have energy equals h c over lambda. So our h, or the Planck's constant, we'll use 6.63. 6.63 times 10 to negative 34 joules second. C is 3 times 10 to the 8 meters per second. And then our lambda, take note it's in nanometers, so we have to be consistent with the units since joule is Newton meter or kilogram meter per second squared. So we have to convert this in meter, and that is 450 times 10 to negative 9 meters. So that will be the energy. It's equivalent to 6.63. Okay, let's solve. 6.63 times 10 to negative 34 times 3 times 10 to the 8 divided by 450 times 10 to negative 9. Okay, that will give us 4.4 times 10 to negative 19 joules. Okay, so that is 4.4 times 10 to negative joules. However, we can express the energy into electron volt. We have energy equals 4.4 times 10 to negative 19. And our conversion unit would be, or conversion factor is 1.6 times 10 to negative 19 joules per electron volt. So dividing them, you will have an energy expressed in electron volt, which is equivalent to 2.7 electron volts. Okay, there. So that is the energy. That is an energy of the photon of blue light. The next item. Estimate how many visible light photons a 100-watt bulb emits per second. Okay, let's assume that it's at the middle of the visible range. So we will be using wavelength 500 nanometers. So let's use that. To solve for the energy, again, we have Hc over lambda. So that is 6.63 times 10 to negative 34 joule second. That's 34. Then we have 3 times 10 to the 8 meters per second divided by 500 times 10 to negative 9. Now the energy is equivalent to is 39.78 times 10 to negative 20. Okay, but what is asked here would be the number of photons for 100 watts. So this 100 watts, recall that 100 watts is equivalent to 100 joules per second. So the question is emits per second, so let's take a look at 100 joules. So we just have to divide 100 joules divided by 39.78 times 10 to negative 20. So our answer will become, we have 2.5 times 10 to negative, or 2 times 10 to positive 20. Okay? So that's 2.5 times 10 to positive 20 photons. So this is an estimation. Okay, next item. While conducting a photoelectric effect experiment with light of a certain frequency, you find that a reverse potential difference of 1.25 volts is required to reduce the current to zero. Find the maximum kinetic energy and the maximum speed of the emitted photoelectrons. So take note that you have here, the potential is 1.25 volts. And then you have Ke maximum is equivalent to electron, or charge of the electron, times V naught. So you have here the charge of the electron is 1.6 times 10 to negative 19. Then multiplied it by 1.25 volts. You will have an answer equivalent to 2.0 times 10 to negative 19. Okay, joules. But take note also that 1 volt is equivalent to joule per coulomb. So we can now have here divided by the charge, and then we can express the Ke maximum by electron volt. So our K, or kinetic energy maximum, is equivalent to 1.25 electron volts. So we can use this to solve for the velocity or the maximum speed. Here we now have kinetic energy equals 1/2 mv squared our kinetic energy is 2.00 times 10 to negative 19. So let's derive an equation for for velocity. We have 2ke over m square root, and then we will have the velocity or the maximum speed of the emitted photoelectrons. So we can substitute square root of 2 times kinetic energy is 2 times 10 to negative 19 joules divided by the mass, 9.11 times 10 to negative 31. So we now have here that will be equal to 6.63 times 10 to positive 5 meters per second. Okay? So we have to use the one in joule so that the units will be consistent. Because joule is Newton meter, 1 joule is Newton meter, is equivalent to kilogram. Newton is kilogram meter per second squared times meter. If you're going to divide it by kilograms, you can now cancel kilogram, and then you will have meter squared per second squared. And then getting the square root of that, you will have the unit of meters per second. Okay, again, the answer is 6.63 times 10 to the 5 meters per second. Okay, next item. Okay, the last item. What is the maximum kinetic energy and speed of an electron ejected from a sodium surface whose work function is W naught, equivalent to 2.28 electron volts, when illuminated by light of wavelength 410 nanometers and a light of wavelength 550 nanometers? So take note that the energy is equivalent to the energy it has is equivalent to HF, or also equivalent to hc over lambda. So c is the speed of light and h is 6.63 times 10 to negative 34 joules second, multiplied it by c, which is 3 times 10 to the 8 meters per second, divided by, if our lambda is 410 nanometers, so 410 times 10 to the negative 9 meters. This amount of energy is equivalent to 6.63 exponent negative 34 Here, our answer here is 1,000. Our answer is 48.51 times 10 to negative 20. our unit here would be joules. But we can express it in electron volt. (48.51 times 10 to negative 20 joules divided by 1.6 times 10 to negative 19 joule per electron volt. So that will give us an equivalent of this is equivalent to 3.03 electron volt. But the question here is the Ke maximum. So our Ke maximum is equal to HF minus the work function. So that one is the potential. The given here, the work not is 2.28 electron volts. So that is 3.03 electron volt minus 2.28. So the maximum kinetic energy here, it's equivalent to 0.75 electron volt. If you have the wavelength is in, if you have a light with a wavelength of 410 nanometers. So that is the Ke maximum. Okay, let's solve for the second part. Let's solve the second part. We now have energy is again HF or Hc over lambda. And H is 6.63 times 10 to negative 34 times C is 3 times 10 to the 8, then divided by the lambda, or the wavelength is 400, or the wavelength is 550 times 10 to negative 9. So we have here 6.63 times 10 to negative 34 times 3 times 10 to the 8 divided by 550 times 10 to 9. The answer here will be 3.6 times 10 to negative 19 joules. Okay. So this is the amount of energy if you have a light having wavelength of 550 nanometers. But let's convert it again to electron volt. So let's divide it by 1.6 times 10 to negative 19 electron volt. So the equivalent would be 2.25 electron volts. Okay? So take note that we have here, in the problem the work function, work not, is equivalent to 2.28 electron volts. So this means that this energy is not enough to remove the electron. Okay? Unlike in the previous situation wherein we have used the 410 nanometers. Okay? So that's it. That ends the second part of quantum theory. Okay, so I will give you exercises on this so that you will be able to solve problems on quantum theory. Okay.